Well, hello. My name is Dave Jewitt, and I'm here to give you a lecture about many aspects of planetary astronomy. I'll do that, but I thought it would be fun, first of all, to give a very quick tour of essentially the history of planetary science. So, you don't have to watch this if you don't want to. I just thought it would be kind of a cool thing to do. Why not? Let me get share screen going. And we'll just run through this fairly fast. I think the reason to do this is to give you some appropriate context for understanding all the different things that have been done in planetary science as a function of time. Okay, and it turns out that this is a reasonable thing to do because planetary science, in many ways, is the original science. It's the oldest science. It's basically the oldest part of astronomy, as I'll tell you right now. And it's been responsible for triggering all sorts of things through the history of astronomy, most importantly, dynamics. The understanding of the dynamics of the stars and the planets comes almost entirely from studies of the solar system. So let's go back. This is an observatory from 5,000 years ago. We moved into the cities about 10, 12,000 years ago. We depended on agriculture. And the observation was made that things happening in the sky correlated with things happening on the ground. And so people just empirically figured out how to use measurements of the sky, where's the sun, where's the moon, to understand when they should plant things in the ground and when it's possible to harvest food from the ground. So the beginnings of our city-dwelling culture are quite closely connected to planetary astronomy, although not in a way that anybody at the time understood, just that the regularity of motions of bodies in the sky, the sun moving across the sky, the moon going around the earth, and even the planets moving relative to the starry background, those things were triggers for making correlations with agriculture on the ground. So there are pretty good connections between planetary astronomy and the seasons and agriculture. People became very mystical. There were connections to religion and astrology. And finally, this cascade of observations led into the thing that today we would call astronomy. And underlying all of this, there's this basic idea that regular things in the sky are good because we can use them for predictions that can help us to survive. And irregular things in the sky are bad. So when a comet appears, that's bad news. When there's a supernova explosion, people are scared. They don't know what that means. Something bad is going to happen. A king is going to die, or an emperor is going to be deposed or something. When there's an eclipse, we also get very scared. So the sky is a source of reassurance, also a source of fear. The idea that we should measure things is amazingly a relatively recent idea. I mean, before the scientific era, which is about 500 years old, people didn't really think that you should measure things in order to understand the world. If you wanted to understand something, you'd go and look in the Bible, or you'd look in the Quran, and then you'd try to figure out what that meant, if anything at all. Of course, it means nothing, but you tried to figure it out in terms of the observations that you made. So the beginnings of the scientific impulse are connected with this idea that we can think about things and understand them through measurement. That's what science is. And one of the first guys, and I would claim the first planetary scientist, is this very famous guy, Tycho Brahe, who lived about 400, 450 years ago in Denmark. And he did fantastic measurements with instruments like the one shown on the right, which is basically just a device for measuring the elevation of a star above the horizon. He could do that better than anybody else. He could measure the position of a star to better than an arcminute, and he did it in a systematic way for years and years and decades. And he built up this body of measurements that became the foundation on which the modern understanding of the solar system was built. Okay, so astrometry done by eye, there's no telescope, no telescopes existed at this time. Astrometry done by eye, by Tycho and some other people as well, is really the beginning of the whole subject, at least in the scientific sense. Now, Tycho was an extraordinary person. He was a great guy, actually. So let's say a few things about him. So we know from the historical record, he was a heavy drinker and a big eater. He was actually an obese guy. He's a fat guy. We also know that he was extremely rich. He owned about 1% of all the money in Denmark. He further convinced the king of Denmark to give him another 3% of the GDP of that country to run his observatory called Uraniborg that you can still see if you go there. He famously got into a duel. He had an argument with a cousin or somebody over some mathematical theorem, and to sort out the argument, they had a duel, and the tip of his nose was cut off. Instead of replacing it with a piece of wax, which is what people did at that time, he replaced it with a brass nose. And so he was a very spectacular looking individual, I'm sure, as they show in the picture right here. He, and I really like this one, he kept a dwarf named Jep under the table. And he regarded Jep very highly. He thought Jep was a clairvoyant. He used Jep to try to predict the future. Just a very amazing relationship there with the dwarf. He also kept a large elk with the horns, and he allowed this elk to get drunk a lot. And in fact, the elk died when it got drunk on beer and fell down the stairs and broke its back. So he was an extraordinary person, and also a bit of a cantankerous person. And he was known to be very stingy with his data. He wouldn't give his data away, even to Kepler. So Kepler was his assistant. Kepler wanted this data. Tycho wouldn't give it. And so that gave rise to the suspicion that Kepler might have poisoned Tycho Brahe. And to sort out that suspicion, people dug up Tycho a few years ago. So there is Tycho. That's obviously the front of his skull. And you can see, that not much of his nose was cut off. Probably the part cut off was just that soft part that didn't cut into the bone at the back. Chemical measurements showed no evidence for poisoning of Tycho. And so the suspicion is, again, based on the written record, that he probably died from some kind of kidney failure. Anyway, so Tycho Brahe is kind of a role model, I think, for planetary scientists. When we grow up, we should all try to be like him. He had a really great life. He did a really large number of interesting things, and he is the foundation person for this subject. The next big development came 1610 when Galileo pointed a telescope upwards. Before that time, it was a military weapon just for looking at the enemy, across the hills or across the sea. Galileo said, hey, let's have a look up. And as soon as he did that, he transformed astronomy, he transformed science, because he moved from the realm where you can only measure the positions of things into the realm of physical study. So immediately he saw things that had never been seen before and that were not allowed to be seen by the prevailing religious orthodoxy of the time. So he saw, for example, the phases of Venus shown in the upper left. Those phases of Venus prove that Venus is going around the sun, not around the Earth. And he saw the satellites of Jupiter shown in those fantastic little diagrams there in the middle left, proving that those satellites go around Jupiter, not around the Earth. So seeing things like that was, at that time, 400 years ago, absolutely revolutionary, absolutely revolutionary. So that's the beginning of the telescopic era and the beginning of the era in which physical studies of bodies in the solar system became possible. Next big development was that of photography. The first photograph of an astronomical object was taken in 1840. You can see it right there. It's an amazingly good picture of the moon, I think, by this guy Draper. And photography moved astronomy and planetary science into a new realm because you could, for the first time, make a permanent record of what you could see through the telescope, okay? And then spectroscopy was added onto that. So you can take a photograph of a spectrum produced by a telescope. And those two things had a big impact on the study of stars, because to understand stars, you really need their spectrum. And so stellar spectroscopy began to take off about 1860 when spectroscopes on telescopes became good. And then cameras on telescopes showing lots of asteroids were good for dynamics of the solar system, because when you have lots of asteroids, you can see things like the Kirkwood gaps. And then you can begin to understand things like resonance, dynamical resonances with the planets, with Jupiter in particular. So what you can see is this consistent theme where technology has an impact on what we know and when we know it. Now, telescopes and photographic emulsions had a much bigger impact on the study of the more distant universe than they did on the solar system. Why was that? Well, partly it's because things in the solar system are moving. Photographic plates are not very sensitive. And so to take a long exposure to see faint things, you suffer from trailing of asteroids. They move across the field and you lose sensitivity. So plates are not very good at imaging faint asteroids. Actually, they're quite bad at doing that. On the other hand, if you have a galaxy that doesn't move, all you do is track the telescope on the galaxy and you can go really deep. So that was done by Slipher and Hubble, and then Lemaitre had a theory about the nature of the universe. And these people discovered essentially modern cosmology. So before the 1920s, nobody knew what galaxies were. We could see them, but we didn't quite understand that they were really far away and that they were part of this expanding universe. That was a major, major discovery of the 1920s. And what it did was leave planetary science in the dust. Because in the solar system, there are not many planets to study. Once you've looked at them with your available technology, there's nothing left to do. All the measurements that people could do that were useful were done. And so the really hot thing became extragalactic astronomy and cosmology. And that remained true through the first half of the 20th century. So planetary science basically died. I mean, it half died in the first half of the 20th century. What brought it back was the invention of the spacecraft, which again is a kind of a political thing, right? These are launched into space essentially by intercontinental ballistic missiles, initially sent up for political purposes, but with great scientific application. So I just show a couple of examples. There's Mariner 4, first one to go to Mars, took that picture at the bottom. Note the rather poor quality of the picture, but at that time, absolutely revolutionary. And then I show, of course, one of the Apollo missions, that's Apollo 10 from 1969. This new focus on being able to go into space revolutionized planetary science and actually restarted planetary science. It brought it out of this dead period. Telescopically, a big change occurred in the 1980s. So the charge coupled device that everybody uses today became a thing in the 1980s. The first picture with a CCD was taken in 1976. It's that picture of Uranus. I forgot to put the date there, but it's a picture of Uranus by Brad Smith. So that was a revolutionary picture at that time. And the big deal with the CCD, as we'll see later on in the main lecture, is the CCD is 50 times more sensitive than a photographic plate, so you can go really faint, and the response is linear. So you can connect the number of counts with the brightness of the object, whereas with a photographic plate, that's horrible. That's a mess, and you can't do that. So CCDs revolutionized the study of the solar system again in the 1980s, as did cheap computing. So before that time, computers were big and expensive and slow, and because of Moore's law, the number of transistors you can pack onto a chip is doubling every 18 months. Computations became cheaper and cheaper and cheaper, so that by 1981, it was possible for Jack Wisdom to establish the existence of dynamical chaos in the asteroid belt. And it began to be possible to run models simulating the evolution of the solar system, and even to some extent, the formation of the solar system, N-body models in computers. And we'll have more to say about that later on. And you probably already heard much more about that from Alessandro Morbidelli in the beginning. Now then, 1992, these two things came together, and there are two observations that are both important for a solar system. First of all, the Kuiper belt was discovered. Kuiper belt relies on CCDs. It would not really be possible to discover the Kuiper belt without, or explore it without CCDs. And it relies on computers because you need computing power just to handle the CCD images. And then exoplanets were discovered at a similar time, 1992, 1995, by a couple of different techniques. Again, relying on CCD detectors in the Doppler planets case, and computing power to analyze the data. So these, first of all, in the case of Kuiper Belt, totally change our perception of the solar system in a way that we'll mention soon. And they then give us a proper context for understanding the solar system relative to planetary systems of other stars. Very recently, we've entered the era of sample return. And the deal here is that when you can bring back a piece of an astronomical object, you can subject it to all sorts of measurements that you can't do from a spacecraft. Now, it's true, we had samples from the moon in the 1960s and 70s, but that was it. Now the mindset is we can go out there and get pieces of things that we're interested in, asteroids and comets, and soon maybe Mars. And we can bring this stuff back and study it in the lab and use all sorts of very sophisticated geochemical techniques to understand chemical and isotopic information that's present in the rocks that we cannot easily get in any other way. So here's a short movie from a Japanese spacecraft that's descending to the surface of an asteroid called Ryugu. This is Hayabusa 2, not Hayabusa 1. Hayabusa 2 was just a couple of years ago. It's going down. It's going to shoot a ball into the surface, going to kick up a bunch of dust and rocks, and then it's going to capture some of that in that black cone that you can see in front of you. Here it comes. Bang. And there are the rocks all flying around. Some of them go up that cone and get stuck in a box inside and then are brought back to the Earth. It's a fabulous movie. Here is a sample that was brought back from the surface of this asteroid, came back a month or two ago, and is now being studied in labs in Japan. And then the future, we don't know what the future is, of course, but a good prediction would be the future is the convergence of astronomy with biology. So the hot topic now is life. We realize that life probably is everywhere, that life is probably something that we could study astronomically, and that by studying life astronomically, whether it be primitive life or advanced life elsewhere in the universe, we can tie that back to understand ourselves and our place in the solar system. So that's a quick overview of things that I would like to talk about in the rest of this next lecture. Okay, so this was a quick intro lecture just to give you a feel for the history of the subject.